Hello, and a virtual welcome to the 13th LISA Symposium. My name is Ira Thorpe. I'm the NASA LISA study scientist, and I'm going to give you an overview in this talk about NASA's LISA activities. You can find out more about NASA's LISA activities at our website, linked here below, and also at some of the other talks during this conference. So why is NASA involved with LISA? Well, it starts with the science. I put here a quote from NASA's science vision document, which you can read in full, the link below. And there's a couple of highlights I pulled out, one of which is that we use the vantage point of space to achieve, with the science community and our partners, a deep scientific understanding. Of course, LISA is a major international partnership led by the European Space Agency, and it provides an opportunity for NASA to achieve its science vision through this partnership. And of course, the target of LISA being looking at the universe beyond, gravitational waves in general, and LISA in particular being the first mission to look at the milliHertz gravitational wave spectrum, provides an unprecedented opportunity to understand more about the universe beyond our solar system. Second reason why NASA is involved with LISA is experience. For over 20 years, NASA has been involved with LISA and LISA-related activities in one way or another. In fact, one of the very early mission concept studies was done at the Jet Propulsion Laboratory's Team X facility way back in 1997. And of course, there was a joint NASA-ESA mission which was run through the 2000s. You see the old logo here in the center, and one of the spacecraft concept designs from Goddard of that era. There was a number of technology developments that were associated with that mission, two of which made it into flight demonstrations. I've shown here is the colloidal micronewton thrusters which flew on ST-7, which was a NASA contribution to the European-led LISA Pathfinder mission, and this thruster system was successfully tested on that mission. A second one here shown as this is the laser ranging processor from the laser ranging instrument on board the US-German collaboration GRACE Follow-On. GRACE Follow-On is a geodesy mission in which two spacecraft are orbiting the Earth, and they use a microwave link to measure the distance between the spacecraft. The laser ranging instrument, as the name implies, uses a laser link to also measure that distance as a technology demonstrator, and it uses many technologies that were developed for LISA, and it represents the first time we've done this kind of interferometry between two separate spacecraft, and it gives us a lot of information for LISA. Also, we did quite a bit of investment at NASA in some of the science, some of the data analysis underpinning LISA. Shown here is a rendering from a numerical relativity simulation of a binary black hole merger that was done at NASA Goddard. And we were involved with organizing the community and participating with the community. And in fact, the 6th LISA Symposium, I've got the group shot here from back in 2006, was held at NASA Goddard. And so if you have, able to zoom in, you might be able to find yourself in there. So there's a number of different ways in which NASA is involved with LISA in the different parts of the organization. I'll start up at the top at NASA headquarters, which of course is responsible for all the formal negotiation of roles and responsibilities, and for establishing and maintaining LISA within NASA's large program. Here's the NASA headquarters building, which was recently renamed after Mary Jackson on a recently renamed street, Hidden Figures Way in Washington, D.C. I'll point out that Paul Hertz, the director of Astrophysics Division at NASA headquarters, is going to be participating in the Space Agency Town Hall on Tuesday, September 1st at the times here below. Two other contacts at NASA headquarters for LISA are Thomas Hams, the LISA program scientist, and Shahid Habib, the LISA program executive. Now I'll move on to the NASA LISA Study Office. This is the organization that I'm part of as the study scientist. Terry Doiron is my counterpart as the study manager, and we are a proto-project who is charged with implementing NASA's LISA activities. This work gets carried out at a number of NASA field centers, including the Goddard Space Flight Center outside of Washington, D.C., where I work, the Marshall Space Flight Center in Alabama, and the Jet Propulsion Laboratory in California. There's also significant involvement at the University of Florida in Gainesville, as well as a number of industrial partners around the country. One of the major activities of the NASA Study Office is to develop technologies which could be candidate contributions to the mission. And one of the major technologies which we are developing are telescopes. These are a little bit different than the telescopes that NASA has developed for other missions in that they are not used to make images. Instead, they're used to send the light across the long links, the 2.5 million kilometer links between the LISA spacecraft and the constellation. If you didn't have a telescope, the light would diffract to the point where you wouldn't be able to collect enough light to make the measurement and to detect the gravitational waves. One of the important things about this telescope is not so much its size, it's only about a 30 centimeter aperture, but is its stability. So this telescope is in the interferometric path, so any deformation or changes in the telescope itself could mask the gravitational wave signal that we're trying to measure. We're looking at an all-glass design, and shown here is just a notional design with the telescope primary, a boom here holding the secondary, and the light would then pass through this hole under the primary and go back to the rest of the payload, which would be provided by Europe. NASA Goddard is leading this design effort with collaboration from L3Harris Corporation as an industrial partner. The second effort for technology development at NASA is in lasers. These are very important, of course. They are the L in LISA after all. And the emphasis here is on a moderately high power, about 2 watts of light, but again on stability. So we use lasers as effectively our ruler that we're using to measure space-time with, and so we need that ruler to be very stable, in particular stable in frequency and intensity. We're looking at a master oscillator power amplifier, or MOPA design, where a seed laser, here's our prototype seed laser, developed by Abo Photonics and Goddard, would provide the light, which is then amplified by a power amplifier. Here's a power amplifier prototype from Goddard and Fibertech. And the entire setup would be stabilized to a optical cavity such as this one, which is actually the one that was developed by Ball Aerospace and JPL for the aforementioned Grace follow-on mission and meets the LISA requirements. A third area of technology development is in what we call charge management. So as we'll hear in some of the other talks, the LISA test masses are freely flying. They're not actually touching the rest of the spacecraft, and they can build up electric charge due to interaction with cosmic rays and the rest of the space environment. That charge can cause forces on the test mass, which could again mask the gravitational wave signal that we're trying to measure. And so we need to control that charge by shining UV light on either the housing or the test mass and changing charge using the photoelectric effect. This technique was demonstrated on LISA Pathfinder and worked successfully. On LISA Pathfinder, we used a mercury vapor lamp, and for LISA, we're planning to use UV LEDs, which are smaller, lighter, more power efficient, and are able to be modulated. So here's a picture of some LEDs under test at University of Florida to understand some of their statistics and behavior. We've also, with University of Florida, developed a prototype driver, which is able to accept the charge commands and provide the right light output. And we're able to test the whole thing in a torsion pendulum facility, again at University of Florida, to understand it in a system context. The two other technologies, which I've already mentioned but wanted to mention again, are the micronewton thrusters, such as the ones that flew on LISA Pathfinder, and the Phasemeter, or the processor, which flew on the laser ranging instrument on Grace follow-on. These allow us, these very high heritage technologies, would allow us to, in the case of the thrusters, steer the spacecraft very precisely, and in the case of the Phasemeter, measure the interferometric signal and extract both the science information as well as some housekeeping information that's important for maintaining the link. Another area in which we're investing in the study office is in the science area. In a way, the data analysis part of LISA is just another part of the instrument which happens on the ground. We take these relatively small amount of data which is streamed down from the spacecraft, and we need to combine all that data and search for the astrophysical signals, and then provide the estimates of astrophysical parameters for those signals so that the other scientists can work to do astrophysical inference and extract the science information that we're all excited about for this mission. So partly what we do is we prototype some of that science and analysis infrastructure. This is done in collaboration with a worldwide community of researchers. Here's an example of a simulated mock data set of galactic binary sources. And just for a few months of data, I'm able to identify a few thousand sources in this catalog in their strain and frequency. Also try to understand the astrophysical context of many LISA sources. So here's shown a simulation done at NASA Goddard of binary black hole merger with gas and some of the radiation that's produced. This is important for understanding potential multi-messenger sources and the astrophysical context for these LISA sources. In addition to this sort of research work, we look at contributions to the science ground segment. So how would the U.S. contribute to this international effort to extract these signals? And as I mentioned, doing some of this basic research to support the development of the mission. Moving on from the NASA Study Office to the NASA Study Team, despite the very similar acronyms, this is an independent organization. It's chaired by Kelly Holly Bachman at Vanderbilt. And it's a group of experts who, as I say, are independent from the study office. They report to NASA headquarters. And they have two main complementary roles. The first is they represent the future LISA user community to NASA. So they help the agency understand what the needs and desires of the community are for this mission. And in reverse, they represent LISA to that community. So they help the broader astrophysics community understand what LISA's capabilities are and how LISA can inform the science that that community is interested in. And those two parts work together to help us build a better mission. Lastly, talk about the LISA Preparatory Science Program. So this is a grants program. It's part of the Astrophysics Division at NASA headquarters. It's also independent from both the study office and from the study team. So this is just a way to build that community and understand different ways LISA can be used. There's been one cohort of awards back in 2018. There's a full detail of all those awards at this link here. Here's some thumbnails from some posters which we had at a poster session at the AAS winter meeting in Honolulu earlier this year, back when we were able to have in-person meetings, and hopefully we will be there again soon. There's a call for a second cohort out now with a deadline in December, I believe, with the details also at this link. So if you're a US-based researcher and you have some research you'd like to do related to LISA, please check out that program and consider applying. I'd like to wrap up now with an outlook. So in the near term, we'll want to, of course, complete all of our technology development activities on any candidate contributions. We'll continue to finalize negotiations with our European partners about exactly what hardware we will be contributing. We'll work to establish a plan for contributions to the science ground segment, to the data analysis and other science activities, and this will include the important data policy questions. We'll work with the NLST and other community organizations in the US to maintain the science vision and maintain NASA's role in the mission, and to continue other research and development activities to support the future LISA user community, such as those activities funded by the LISA Preparatory Science Program. And with that, I'd like to thank you for your attention and wish you all the best for the rest of this virtual conference. Thank you.